Hello and welcome to the actual final IB Math speedrun of this book with me, Vince. So in this speedrun, we're going to be going through the final test paper, which is the paper 3, which is a bit more about investigation. So let's jump right in. So since I'm only doing like alternating questions and there are only, well, 2 questions here, I guess I'll start with the first one again. And this will be the first and last question of the speedrun. So let's go. So first, we have consider a sequence with first term u1 defined by a recurrence relation of the form u n plus 1 is equal to a times un plus b, where a and b are constants. For each of the given criteria in parts A and B, first, state the type of sequence defined by the recurrence relation. And next, write down an expression for un in terms of u1 and b. And third, write down an expression for the sum of n terms, the first n terms in terms of u1 and b. So the first case is a is equal to 1, the second case is b is equal to 0. A is not equal to 1 and a is not equal to 0. Then the towers of Hanoi. Let's solve this part first and then we'll move on to the later parts. So we have the sequence, the recursive sequence, first term u1 of un plus 1 is equal to, and then a is 1, so this is u1 plus b. So what type of sequence is this? This looks like a linear sequence, just adding one number over and over again. I guess it's a arithmetic progression, because we have u to the n is equal to the first term plus some constant. So expression for un, so un in this case would be equal to u1 plus, I guess, n minus 1b. It's just an arithmetic series. And then the sum of the first n terms would be equal to n over 2 times u1 to u1 plus n minus 1b. Yeah, because that's the sum of an arithmetic series. Nice. So next question is when b is equal to 0, a is not equal to 1, or a is not equal to 0. So we have the next term is equal to an. Interesting. So this is a geometric sequence, and therefore un is equal to sorry, not a to the n, a times un would be equal to u1 times a to the n minus 1. And so the sum of the first n terms would be equal to 1 minus this geometric series. This would be u1 times 1 minus a to the n, 1 minus a to the n over 1 minus a, I believe, is the geometric series sum. A to the n minus 1 over a minus 1. Yep, so that's the sum. And so next part of the question. So the next part is the Towers of Hanoi is a famous example of a sequence defined by a recurrence relation of the form u of n plus 1 is equal to a times u of n plus b. In this sequence, the first term is equal to 1, and the next term, each time, is equal to 2 times u to the n plus 1. So first is find the second term, the third term, the fourth term, and the fifth term. Next, using your answers to part I, suggest an explicit expression for un in terms of n. Excuse me. And then finally, prove your expression from part 2 using mathematical induction. Cool. And then there's a fourth part, but let's solve this part first. So we have the n plus 1 term, or the next term, is equal to 2 times u to the n plus 1. So this means the second term is equal to 3. The third term is equal to 2 times 3, 6, 7. The fourth term is equal to 15. And the fifth term is equal to 31. So, using your expression to suggest an explicit expression. Well, what are we doing here? So we are increasing by 2, 4, 8, 16. So it looks to be the expression of 2 to the power of n minus 1. So prove it using mathematical induction. So for the first step, we need to prove that 1. So basic step is we need to prove that 1 is equal to 2. Or actually, I mean, yeah, I guess 1 is equal to 2 to the 1 minus 1. That would be the first step. Yep, so this gives that the first term is equal to 1. And then, assuming that this is true, we now need to move to the inductive step. So, which means that we assume that this is true for some n, and we need to prove it for the n minus 1. So we need to prove that the term of n plus 1 is equal to 2u times to the n plus 1. And so, well, we know this term is equal to 2 to the n minus 1. So this is equal to 2 to the 2n minus 1 plus 1, which is equal to 2 to the n plus 1 minus 2 plus 1, which is minus 1. So therefore, u to the n plus 1 also equals 2 to the n plus 1 minus 1. And so therefore, by the process of mathematical induction, this statement is proved to be correct. Very nice. Okay. Next one. Sorry, there are actually 2 more parts. And so the next part is when a is not equal to 1, the recurrence relation u of n plus 1 is equal to aun plus b can be rewritten in the form u of n plus 1 plus a constant is equal to a times u of n plus a constant for some constant c. So first, find c in terms of a and b. Next, write down the recurrence relation for the... Oh, wait. No, so there is another one. So a new sequence is defined by v of n is equal to u of n plus c. So write down the recurrence relation for the sequence v of n and state what type of sequence v of n is. Next, hence write down an explicit formula for v of n in terms of v1, a, and n. And finally, hence write down an explicit formula for u of n in terms of u1, a, b, and n. Okay. So find constant c. So we know u of n plus 1 is equal to an plus b, to a times u of n plus b. And we're saying that we can rewrite this in the form u of n plus 1 plus c equals a times un plus c. So a times u of n plus b plus c is equal to a times u of n plus a times c. So we can cancel those out. So we have, sorry, this is just a times c. So we have b is equal to ac minus c is equal to c times a minus 1. So c is equal to b over a minus 1. Okay. So we have write an explicit formula, new sequence is v of n is equal to u of n plus c. So v of n is equal to u of n plus b over a minus 1. U of n plus c. So since u of n plus c is equal to u of a times u of n minus 1 plus c, but this is equal to again v of n minus 1. So this is equal to actually a v of n minus 1. So this is actually just a geometric regression. Okay, interesting. So write down an explicit formula for v of n in terms of v1, a, and n. So of course, explicit formula would be v of n is equal to v of 1 times a to the n, because that's a geometric formula. It's n minus 1, and so hence write down an explicit formula for u of n in terms of u1, a, b, and n. So we know this is un plus c is equal to v1 times a of n minus 1. And v of 1 is equal to u of 1 plus c. So we have u of n plus c is equal to u of 1 plus c times a to the n minus 1. And u of n is equal to u1 plus c times a to the n minus 1 minus c. So this is equal to plus c times a to the n minus 1 minus 1. Sorry about that. I was very confused because I thought we got the answer wrong, but apparently the answer is actually just this. So if we backtrack a little, we need to find this in terms of u of n. So u of n plus c equals u of 1 plus c times a to the n minus 1. U of n equals u of 1 plus c times a to the n minus c. And so if we need to write it in terms of u1, a, b, and n, we can rewrite it as u1 times a to the n minus 1 plus b over a minus 1 times a to the n minus 1. So yeah, that's correct. This should be correct. And so finally, the last question, E, asks us to verify our answers, this answer with the Tower of Hanoi. Because remember, the Tower of Hanoi had a is equal to 2, b is equal to 1, and u of 1 is equal to 1. And so we need to verify that this thing evaluates to 2 to the n minus 1 if we plug all of the numbers in. So let's do that. So that's 1 times 2 to the n minus 1 plus 1 over 1 times 2 to the n minus 1 minus 1. And so since, of course, we're adding these two together, this is equal to 2 times 2 to the n minus 1 minus 1. And so this is equal to 2 to the n minus 1. So indeed, it is the same formula. So yeah, well, that was it. It's been an interesting journey, and I hope you stuck along. If you've stuck along to the very end, thanks for watching, and that will be the final IB Math speedrun. See you sometime.